Aloha, Richard Halverson here. This is ITS 148, and today is March 2nd, Tuesday, and we're in like the 8th week or something like that. Let me share my screen. Okay, ITS 148, and we are in we're in the second. Okay, so I went over, recursion took longer than I thought, and my intention was last week I was going to start chapter 15 last week, but what happened, I scheduled 2 classes, you may remember, but what happened was I recorded the first class and I didn't get to the labs. So in the second class, I did the labs, and then I just merged the 2 videos together. So this class 7 is actually consists of two labs that were, or 2 videos that were merged together. Let's see. Hello, Richard Halverson here. This is ITS 148. And today okay, so yes, we had February 23rd there, and then this is about the 7th recording. At the end is less than. I recorded the that's the labs. Okay, so and then I spliced them together. All right, so so this week we're going to start chapter 15, and it's chapter 15 I think is a really important chapter because we start talking about analyzing the computational complexity of the algorithms. Okay, it's a fancy multi-syllable term there, but basically it's how computer scientists decide what algorithm, if a particular algorithm is better than another algorithm. For example, there's probably about 10 good sorting algorithms, and they all have different computational complexities. And so depending on what the data looks like and how the data is coming, each of them has their advantages and disadvantages. So sorting are good algorithms to learn about computational complexity. So anyway, let's get started. We're in chapter 15. So we just finished recursion, and now we're going to revisit search algorithms like linear search and binary search, and sorting algorithms, and we've seen them before, but this time we're going to look at them from a little bit more analytical point of view. So if we start out with linear search here, you know that the task is to locate if a particular item is in a list. And so for linear search, the algorithm is just to look at every item, go through the list and look at every item until you either find it or you get to the end of the list and you didn't find it. Okay, so that's the linear search. The worst case for a linear search is that you have to look at every item and then you end up not finding it. The best case is if the first item you look at is the item that you're looking for. Okay, so this just demonstrates that it's looking for 11, and it's going to go all the way through and not find 11. And so anyway, and this is a description of the algorithm. Okay, let's say we have a list. This list happens to be sorted, but for a linear search, the list doesn't have to be sorted. It can be any list. So this prints them out. So this is the list. And then it asks the user for something to search for. And then as long as the user doesn't type in a -1, where's linear search? Where does it ask it? Oh, here it is. Right. No, the -1, what comes back from the linear search. So the linear search algorithm is here, and this is the list of numbers, and this is what we're looking for. And so we search through the whole list, using its index, 0 through the length -1, and we look at each one, and if we find the key, then we're done, and we return the index. In other words, which index it is. Otherwise, if we get all the way to the bottom, then that means we haven't found it, and then we return a -1. Okay, so that's linear search. So so if we look at this concept of algorithm runtime is basically how long it takes for the algorithm to execute, where you assume some certain time period per step. Okay, and it's kind of, it depends on all kinds of things, comparable steps. But if we just assume a step is a step, and so let's say each one takes 1 microsecond. So there's a million microseconds in a second. There's not 1,000, there's a million. And for linear search, if you're searching through something that's got 1 million elements and it's not in there, it's going to take a whole second to get through it. Okay, so if it's 10 million elements, then it's going to take 10 seconds, and so on. So the algorithm, so an algorithm typically uses a number of steps proportional to the size of the input. And the thing is the thing you're trying to determine is what is that proportion. How do you express that proportion? And for linear search, it's linear. If you double the number of elements, the amount of time doubles. If you 10 times it, the amount of time 10 times it. The amount of time is multiplied by 10. All right, so that's so here it tests if you understand that, by multiplying this by that. Now, binary search is different. A binary search, first of all, takes the list has to be sorted. So it takes advantage of the fact that the list is sorted, and then you also know how many elements there are on the list, so you know how to index each one of them. So the indexing is 0 through the number of elements -1. That's indexing it, and it doesn't take any. You can index any element in the list in the same amount of time, in a constant amount of time. So it's not a list where you have to start at the beginning, and if you want to get to the 6th index, you have to go through 0 through 5. It's you can just go directly there. So that may seem like a not very important point, but there's lots of ways to represent these data structures. So for binary search to work, we have to have those characteristics. Whereas for linear search, it doesn't. Those requirements weren't there. But with a binary search, you start by looking to see in the middle of the list if that's the element you're looking for. Now, it's either going to be the element you're looking for, or the element you're looking for is going to be less than that. Remember they're in order, in some kind of order, or the element that you're looking for is going to be greater than the element that you first looked at, which is in directly in the middle of the list. And then so then that means the next search, you've narrowed down, you've cut down the number of elements that you have to look for the second time, because if it's bigger, If the element you're looking for is bigger, then you've already eliminated, the lower half. And then you do the same thing. You split it in half and you eliminate half, or you find it, you split it in half, and you either find it or you eliminate half, and so on until you get down to one element, because each time you're splitting it in half. And then that last element that you look at is either going to be the element you're looking for or not. And if it's not, then you know it's not in the list. So worst case is still looking the worst case number of times, but it turns out that with the binary search, the worst case number of times is not the number of elements in the list. It turns out it's log to the base 2 of the number of elements in the list. Now, log to the base 2 might sound too mathy for you, but I'm going to draw the representation or show you the relationship between a power of 2 and log 2, and it's actually pretty easy. So when we get to that point, I'll do that. So this shows an example of a binary search searching for somebody, and each time, so we're searching for Puja, and so each time we split it in half, and we're either going to the lower half or the upper half, and we either find it or not. In this example, we found it. You can look through that more. Here's one where the binary search efficiency searches a sorted list by reducing the search space in half each time. That's exactly what we see up here, but this is using numbers. So here we start. Where's the description? Here's a description. Here's the algorithm. So this shows clearly, more clearly, how the algorithm works. So we start by setting a low value and a high value, and it starts out with the low value is the lowest point, the lowest index, and the high value is the highest index. And we're looking for a 16. So let's go. And so the first thing that happens is we split it in two and we figure out what the middle element is. And by the way, this is a good example because we see what happens when there's an even number of elements and we have to split it in half. Okay, so there's not a center element. So we'll see what it does. So the first thing we do is we figure out high plus low divided by 2. And so high plus low is 7 plus 0 is 7, divided by 2 is 3.5, but it's integer divide because we're looking at indexes. So it's 3. So that's the middle point. So then we look at the middle point and we see, is that 16? No, it's not 16. So then what happens? We know it's in the upper half. So then we make the new low be 1 higher than the old mid. See that? So the old mid was 3. And since 16 is higher than 14, we made the new low be 1 higher than mid. Okay, so now low is here and high is here. And we figure out what mid is by doing 7 plus 4 is 11 divided by 2 is 5. So that's this. So this is the new mid. And then we look to see, is mid is 24 equal to 16? So there's that test. It's less than, so that means it must be to the left of 24. And so you might have missed it, but it set the new mid as down below and down 1. So all 3, it set the new high as down below 1. So all 3 lined up to index 4, and I looked at index 4, and it turns out that's what it was looking for. And so it turns out it only takes like 4 steps instead of going through all of them. All right, so here's the actual algorithm. It's the same thing. We read in some numbers. Notice now this time they're also sorted. Print them out, and then we do the binary search method here. And so so this is the list, the sorted list, and this is what the one we're looking for. And here is where we initialize low and high. And then while high is greater than or equal to low, we either while high is greater than or equal to low, in other words, that's what it should be. High should be bigger than low, or equal. It should never be where low is greater than high. If low is greater than high, then we've missed it. Then it's not in there. And if low is greater than high, then it's just going to return a -1, which means it's not in the list. But as long as low is not greater than high, then we calculate a midpoint, and that's what we look at. That's the element we look at. And the element that we look at is either going to be less than the key, in which case we make the low one higher than the mid, or the element that we look at mid is greater than the key. If that's the case, then the point we're looking at is greater than the key, so we have to set a new high equal to mid. Is that right? It's like I'm getting these two mixed up in my head. Anyway, you reset the high point if the number otherwise, if this is not true and if this is not true, then that means they must be equal, which means we have actually means numbers of numbers of mid is equal to key. So we found the midpoint. So anyway, so you can see that each time we either set the low to one higher than the mid, or we set the high to one lower than the mid, and that's what divides the list in half each time as we're stepping through this. Okay, so for efficiency, we see that because we cut it in half each time, we get down to only looking at one element a lot quicker, or looking at the last element that we're going to look at a lot more quickly. And it's not the last one in the list either, which is how a linear search would work. It's someplace, some distance from the middle, from how far down you have to go to actually identify that as an index, till you actually look at that as an index. And it turns out that it's log to the base, it's log of n to the base 2. So if we have 32 elements, let me put up my whiteboard here. So I'm only going to try to get to the beginning of the sorting section today. All right, so let's say we have a 32 element list. Okay, so it turns out that 32 element list means we've got 32 elements. Turns out that 2 to the 5th power is 32. Log to the base 2 of 32 equals 5. Okay, so that's the relationship. So if you want to figure out what the log of a number is, you think in your head what the closest number is to some power of 2. you know, where 2 to the 1 is 2, 2 to the 2 is 4, you know, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, you know, that's 64 is 2 to the 6, 128 is 2 to the 7th, and so on. 2 to the 10th is 1024. 2 to the 20th, coffee. 2 to the 20th is, it's about a million. This is 2 to the 10th is about 1,000, and 2 to the 20th is about a million. Let me look at my, let's look at my calculator here. 2 to the 20th power. Can I do powers on this? I think maybe I can, but it's 2 times 2. Can I just do this? Yeah. Okay, 32, 64. Okay, that here's 10 to the 10th, 11th, 12th, 13, 14, 15, 16, 2 to the 16th. That's as high as I remember memorizing them in 2nd grade, up to 2 to the 16th power. And then 2 to the 17th, 2 to the 18th, 2 to the 19th, 2 to the 20th. See, so 2 to the 20th is about a million. So if you know that 2 to the 20th is about a million, then you know that log to the base 2 of a million, can I do? So log the base 2 of a million is about 20. Turns out that what did we say that? Well, it's this 1048 576. 1048 576. Okay, so that's kind of how you remember. So when anybody asks you, well, you know, how long? Okay, so a linear search for, you know, you can keep on going to a billion. Turns out 2 to the 30th is like a billion. So this is 2 to the 20th, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. See, that's about a billion. So a linear search would take on, it says, to say you have a billion elements in your list, a linear search would take on the order of a billion, you know, steps, whereas a binary search, as long as it's sorted, a binary search would only take 30, because it's log to the base 2. Log to the base 2 of a billion is, because 2 to the 30th is this. That's so log to the base 2 of a billion is 30, about 30. Anyway, so that's how I remember it. All right, so this is and it's actually +1 because there's one more. So we're counting steps. That's what this is all about. It's counting steps, and how does the number of steps change when the size of the input changes? And we're looking at like order of magnitude kind of stuff here. We're not looking at exactly. So you'll see when we start to look at the efficiency of algorithms, we drop out the constants, we drop out the smaller terms, and we just focus on the biggest, you know, n. Is it n? Is it log to the base 2 of n, or is it n? Like for linear search, it's n. Or for sorting, it can be n squared. So if you know, so that's what we're looking for here, and that's the sort of analysis we're going to be doing. Okay, so here we are introduced to it. It's called O notation. Big O notation. If this makes good sense to you, and you kind of like the idea of thinking about the big O, it's called big O notation when you're writing algorithms, and you know you want to you know, you have the value that you want the big O to be as low as, you know, it can be, then, you know, you're more of a computer science algorithms kind of person, and maybe you should think more about getting a job or, getting a bachelor's degree and going and working someplace where you're writing, you're applying more sophisticated algorithms to solving problems. And I think, I'm not a gamer, but I'm quite sure that writing games requires this stuff because, the faster it seems to me that speed in games is very important. Okay, I'm not a gamer. I always wanted to write a program that was going to make me money, but I never thought of gaming as a paradigm because I'm too old to Pong is where first computer game that I ever learned. But is big O notation? Yes, it's often used. Yeah. If you can talk about big O notation, if you understand big O notation, then you're one of the smartest programmers in the room. So, if you understand how to compute it, it's simple. You apply these rules, and this book is very good at expressing that. One difference between, let's see, okay, so if you get your bachelor's degree in Bachelor of Information Technology at UH West Oahu or Maui, and let's say you want to go to graduate school in computer science, okay, they will say, they'll tell you that you have to take ICS 311. And ICS 311 is sort of beyond ITS. Well, it's beyond ITS 1, it's beyond this course, but it's this course is a lot like ICS 211, but not as rigorous. If you take ITS 228, then we're going to get into the rigor of 211 and get into a little bit more of the 311 stuff. But 311 is all about O notation, and you learn all the different kinds of algorithms and all the different data structures that computer scientists use to solve all the problems. And it's usually some sort of tree thing, some sort of tree with a characteristic or recursive. Some of the algorithms may be recursive, but it all boils down to the big O notation of worst case and average case of traversing through that huge graph or tree to figure out what the best next move is, whether you should shoot that guy or this other guy, I guess, or something, I don't know. But yes, big O notation. It's so that's why I kind of spending more time on this than you might than what seems to be important. Big O notation, understanding big O notation doesn't help you code faster. It doesn't help you, once you know the algorithm, to get it running faster. But what it does do is you're presented with a you could be presented with a problem where it's some sort of existing program, and you were just hired as a programmer, and this one part is just taking too long to execute. It's not finishing in time, and it's causing some other things to slow down, or some things getting out of order or something. And so you got to go in there and look and see what it does and figure out how to make it faster. Well, you're going to do a little bit of maybe making some of the loops more efficient, but the first thing you should probably do is look and see if there's any way that you can turn some sort of search into a binary search. Or you can, the trade-off is you have this big list, and you can either do a linear search or you can sort it and do a binary search. Well, sorting takes O of n log n, best case. It's O of n times log n, so log to the base 2 of n. So that's worse than O of n. So if you're only going to do it once, maybe it's best just to do the linear search. But if there's anything where you may reuse that list and have to do it again, even if it's a different list, but it's only you're making some additions to it, you're inserting new data in, you may want to do that. So it's not intimidating if you just follow these simple rules, and it's kind of simple. I mean, they kind of go through this, and it's like, well, you can just see what the answer is, usually. Okay, so big O notation is a mathematical way of describing how a function generally behaves in relation to the input size. So in big O notation, all functions that have the same growth rate as determined by the highest order term of the function are characterized by the same big O. So for example, okay, so given a function that describes the running time of an algorithm, big O notation for that function can be determined using the following rules, simple rules. The first one is if this function is a sum of several terms, you only look at the highest order one. Now we're seeing, okay, so here, the highest order one is you got a 5, you got a 13 times n, you got a 7 times n squared. Well, the highest order one is just n squared. Okay, now you're probably thinking, well, how do you come up with this? Well, don't worry about that. Okay, you're probably never going to be looking at an algorithm and deriving this thing. This looks like a pretty complicated thing. It's going to be much more simpler, but you'll get the idea, and then you'll see that if you really had to, after you do this a few times, if you really had to, you may analyze an algorithm and it ends up being something like this, but you probably would not even analyze it. You'd look at the algorithm, you look and see, oh, there must be a loop inside of a loop, because that's why it's n squared. You get the loop inside of a loop, and then you look there and okay, that's my n squared, and how can I make this more efficient? And maybe you won't bother. Maybe you reduce this and you end up increasing this, and it ends up overall being better, especially for large sizes. But anyway, so here we take the biggest term, which is 7n squared, and then we drop off the constant. So it's just n squared. So you look at this, oh, it's just this, So it's now this is a constant, so we can drop off the constant. If it's something else, if it's like log of n, then you would not drop off that. You'd leave it there. All right, so that's how you determine the big O. So we see this. Which of the following big O notations is equivalent to this? Well, you drop off the constant, so it's n. It's just O of n. That's it, O of n. Okay. Which of the big O notations is equivalent to this? Well, you drop off the constant there. It's just n. And then, which of the following big O notations is equivalent to n cubed? N cubed, oh, it must be n cubed. Okay, so it's easy. This is sort of a mathematical way of saying, like, if you got something and then you got something and you're trying to multiply it by you already have the O of it. It's just, it's multiplying. It's the O of. It's pretty obvious. You'll see when we do it. Determine the simplified big O notation. Okay, so this is just a constant times that, so it's should be this, I think. Yes. This is just you're just adding. What's the difference between this one? Oh, this is multiplying. This is multiplying. This is adding. It's even more so. Just this. Okay, this is n. N times O of n squared. So that's n. That's this one because you're multiplying it by an n. N times n squared is n cubed. More or less. Yeah, it is. Here we're adding, so it's just the biggest term. It looks like this is the biggest term. It's just the biggest one since we're adding. So I think it's this one. I don't think this matters. I think this is just gonna, n cubed is gonna drown out the n squared. I think it's this one. I could be wrong. And here it's just, this is log to the base 2 of n, so it's, we dropped the 2 because it turns out that log to the base 10, okay, it turns out you can get to them using just by constants, like, I think it's like, you take log to the base, you take, okay, so a million, as you know, a million is, let me resell this. So a million is about 2 to the 20th power. Log to base 10 of a million is 6. That's exact. You know, log to the base 10 of a billion is 9. Log to the base 10 of 1,000 is 3. Log to the base 10 of 100 is 2. Log to the base 10 of 10 is 1. You know, so that it's just the number of zeros. So 6, and actually, you know, this is in binary. This is 1 followed by 20 zeros in binary. It turns out, but so log the base 2 of a million is about 20, right? Well, so it's like the factor is like 20 over 6. So it turns out that you can go between these logs by just multiplying it by a constant. Okay, so that means the difference between the logs is a constant, which means we can just drop the 2. You know, it's like log, we just log n. We just say log n because the difference between log n, where n, you know, log 10 of n and log 2 of n is just a constant. It happens to be 20 over 6, and it works with, you know, bigger and smaller numbers also. All right. So anyway, and so here's the growth rate, and this is a good chart. They figured it out, and they just demonstrated this. In fact, you could write a program to generate this if you wanted to. You just find some log n. You find some log n function, and you run it a zillion times, and you get you know, you get these numbers depending on some constant times these numbers. The fact is, though, for log to the base 2 of n, if you go from 10 to 100, in other words, you're 10 timesing it, you're only, the program is only going from 3.3 microseconds to 6.6 microseconds. You see, you're 10 timesing it, but you're only doubling the amount of time it takes to run. If it's n, of course, if it's you 10 times it, you 10 times it. So it takes 10 microseconds here, it takes 100 microseconds. So it takes 10 microseconds with 10 of them. It's going to take 100 microseconds with 100 of them. For log to the base 2 of n, it's only, you know, it's smaller, but it's going to, if it's for 10 of them, it's, or for 100 of them, it's only twice longer than for 10 of them. For n log n, and these are the good sorting algorithms. The good sorting algorithms are n log n. It's a little bit, it's, you know, it's more than n. From 10 to 10, you know, it's more than 10 times 10 times. It's, you know, this is a you know, this is much larger than 10 times this, and so on. N squared, we're starting to see things grow exponentially. If it's here, it's n squared, it's 10. Is this right? Second. Is this point? Oh, this is point. Okay, that makes, there's a point, there's a decimal point there, and there's no decimal point there. Okay, so here we're going from 0.1 all the way to 10. That's 100 times. 100 times this gets you this, and 1,000 times this gets you this. So yeah, and so here, you see here is, this is 2 to the n, and there are 2 to the n algorithms out there, All right, so this is why figuring out where your algorithm sits in this, it's going to be like one of these. It's not, I mean, it can be in between somehow. If you might do n time, you might do, n log n squared or something, but it's basically one of these. And so it'll follow, a profile that looks kind of like this. And depending on like the range of the input, you may want to, change how you're doing something, change an algorithm. So anyway, this kind of shows the growth. This is n squared. This is n factorial, I guess is the biggest. So common big O complexities. Here's examples. Okay, so these are Python programs, I guess. So O of 1 just means constant. It doesn't matter how. Okay, find the minimum. In this case, it's just going to take 1. It's constant. It's tough to see how. Yes, if it's just 1. An example of an O of n log n is, example of an O of log n, of course, is binary search. Example of O of n is a linear search. Example of n log n is a merge sort. You have to look at every element, but and you have to do kind of like an equivalent of a binary search kind of thing for every element. So you can see that it grows faster than this, but it doesn't grow as fast as this because this is n times n. This is n times log n. So the more simple sorts that we cover, selection sort, bubble sort, insertion sort, and selection merge. Well, anyway, those are there's variations of bubble and so on. Those are all n squared because for each element you basically go through the list again. Now, as you go along, the going through the list again can become smaller and smaller, but still it's on the order of n times n, so quadratic. Yeah, Fibonacci here's an example of a recursive algorithm that ends up being exponential, calculating the Fibonacci numbers because you have to calculate the Fibonacci anyway. So that ends up being exponential. It's kind of hard to envision it in your head. It's not so necessary that you do. All right, so here's understanding these terms: constant, linear, and exponential, log linear, and logarithmic, and so on. And you can figure those out. Let's see, algorithmic. Okay, I think this is, yeah, and after this we're getting into sorting. Okay, so I'm going to do this section and then briefly touch on the next section, and then we can, this class is going to meet again, as you saw from the, on Thursday. So we look at generally worst case, average case, and best case for algorithms. And for average case, you usually need some sort of understanding of the statistical properties of the data as it's coming in. So for example, finding the maximum value using a linear search. Oh no, just finding the maximum value. Worst case can take one operation plus n iterations. Okay, so we have a list of numbers. It's got n. There's n elements in this list, n numbers in this list, and this for loop is going to, iterate. There's going to be an operation for every one, and exactly one operation for every member in the list. And then there's also going to be this if statement, which is going to be, that's an evaluation. It's going to evaluate if the number is greater than the max value, and if it is, then it's also going to execute this max val equals num. It's not. If num is not greater than max val, then it does not execute this last assignment. But if we're looking at worst case, we're going to assume that that's executed every time. And basically, what it is if this list is already sorted, and you're looking for the maximum value in a sorted list, starting at the beginning of the list, this max val variable is going to be reassigned, for each one. So that would be the worst case. The best case would be if it's a reverse sorted list, and the first element that comes across is already the maximum value. Then this max val equals num would never be executed, and that would be the best case. But anyway, so to figure out the worst case, okay, so here we're actually counting up the steps. Okay, there's one step, which is this first assignment, and then there's this one step, because for everyone you're going to do this for, that for, and that's an operation. It's actually quite a bit of an operation. You're incrementing an index. And you're testing to see if the index is past the end of the list. If it's not, then you get a number and store that into this num variable. So the actual execution of the for part there is actually, can be thought of as more than one operation. But in this example, we just think of it as one. And so that's this one, and then plus 2 means the if is going to be this is going to be evaluated, and then the assignment is going to take place, and that's 2. So we have 1 plus 3n. Well, again, it's just the biggest factor, the constants drop off, and it's OVAD. So the worst case time analysis for a linear search is OVAD. That's the worst case. So here we're just going through and seeing that we understand this. Which function best represents the number of operations in the worst case? Well, here, worst case is every one of these gets executed. Every one of these gets executed. So it's going to be 1 plus this one plus this one. So I guess it's this one. And what's the big O? Okay, this is for a different one, but there this extra stuff drops off. So I can already say it must be this one, because this would not be in a big O notation, and that's not even big O notation. So I'm sorry, I'm gonna guess and put that one down. And here it shows the actual calculations, or how we come up with that. So you can see what we're learning here is actually how to compute the big O step by step. You know, you add up all the steps and you do this, and then you redo, you get rid of the constants and so on, and then you end up with just the O of n. But you can see that it's pretty easy just to look at it and see where it is. What is the big O notation for this worst case? Okay, so I is going to go, you know, from 1, 2, 3, 4, 5, 6, 7, 8, 9, however high n is, and if we're going to look at the mod to the base 2 of I when it's 0, that means half the time. So this is going to be executed all the time, but only half the time this is going to be executed. Well, I don't know. It's this. It's here, yeah. So this gets executed once, this gets executed once, and this gets executed half the time, and that would be this here. It looks like. All right. So anyway, you can do these. Okay. Well, let's go on. Okay. So what is the big O notation for the worst case runtime? This is once. This is once. Oh, let's just look at it. Oh, each time. Okay, n val is n, and each time we're dividing by 2. Look at that. Each time we're dividing by 2. Yes, until we get down to 0. So I bet you it's this one. N val is decreased by half each iteration, so the loop will execute log to the base 2 of n times. All right, what's the big O for the best case? Okay, this is best case. So this executes once, this executes once, and this fails. This doesn't get executed at all, and then this executes. So this. All right, counting constant time operations. I think the point of this is basically when we're talking about constants, constant time operations, they all kind of reduce down to O of 1 because it's constants, and constants are omitted from big O notation. So we end up just ignoring them. Counting the number of constant time operations in a finite sequence is not needed. So for num in numbers, so I think n iterations. O of 1, O of 1, O of 1. That's n iterations of O of 1. Yeah, right. That's what I thought. Okay. That's what I thought. This. All right. So here, this is just the complexity of the algorithm is O of 1. It's just looking at that. It's just looking at this. It's figuring out what toll amount is based on time hour. So it's just, this is O of 1. What is this for? a for loop of the form that that does not have nested loops or function calls and does not modify num in the loop will always have a complexity of O of n. Yeah, I guess if n is the number of numbers in numbers. And the complexity of the algorithm below is O of 1. But this is a constant. This is a constant. So it just figures out. So this is true, I think. Yes. So here we're starting to learn, talk about runtime analysis of nested loops and how they can end up being O of n squared. And that's exactly what happens in when we're figuring out how long it takes for sorting algorithms. These are this is a nested loop. This can range up to n, this can range up to n. Is this? Yes, this is also O of n. So so for sorting, so let's just, this is just the introduction to sorting. So let's go through this. It's 11:30 already, but so this is where we are right now. It's an introduction to sorting, and then we're going to cover selection sort and insertion sort, and these two sorts are O of n squared sorts, where we start with one and then we scan through. We're first for this one we sort by swapping. Here, let's just quickly do this. Sort the numbers from smallest on the left to largest on the right, and select two numbers and then click swap values. So select two numbers and then click swap values. Okay, well. Okay, now I've got 2 in the right place. 7. Oh, what if I just do this? Can I do that? Oh, now I've got 7 in the right place. And then I want 41 is next. So I'm going to swap these two. And then 47 is next. So I'm going to swap these two. Oh, and we're done. All right. So that's one example of sorting. And the way that sort worked was I started at the first one. How do you reset? Let's reset. I start at the first one, and I scan all the way through the whole list and find the smallest one. And if that smallest one is smaller than the one I'm looking at, then I swap them. So I'm going to go through. I'm trying to find the first one here. So I go through the whole list, and I find 10 is the smallest one. So I'm going to swap 10 with 32, and I get that. Now I'm going to find the one for the next one down. Go through the whole list, find the smallest one. It's this one. So I'm going to swap. And then I start with the next one, and I go through the whole list and find the smallest one. It's this one. And then I go through the whole list and find the smallest one, and it's this one. And then the smallest one is this one. And then I'm done. So that's one way to do it. There's other ways where I can start by doing pairs. Let's see. So I can start at the bottom, and I can bubble up the smaller one. So this pair, 33 is smaller than 56. So I'm going to swap them. And then I'm going to go this 33 is smaller than 53. So swap it. And then these two, 33 is smaller than 53. So swap it. These two is fine. These two is fine. these two, 21 is smaller than 45, so swap it. Okay, now I know I got the 21 in the right place. That's all I know. So we can go all the way back up and start again. 56 and 53 are fine. These are fine. 53 and 53 is fine. 33 and 53 is fine. 27 and 33 is fine. 45 and 27 is not fine, so swap them. Okay, and then we go down to the next one. See, so that's a bubble sort. That's a different kind of sort. But still, we start with one and we go through the whole thing, and then we go to the next one, we go through the whole thing, and so that ends up being n squared. So anyway, I've talked enough, and thank you for staying late. And do you have any questions?
Memorize it.
Yeah. Well, I'm gonna in this class, I'm gonna you know, always mention the big O, just so we get used to it, and then I think you'll get used to it, and it'll just be something that you can just kind of see in an algorithm. Because you'll
I guess it kind of just goes in my subconscious, and then it comes out when I use it, or if I practice it enough. Because I tried to memorize from the last class everything, and then I forgot it in between, and then I went back to it and picked it up again. So I'm trying to just not stress too much about memorization.
Yes. Yeah, you learn by doing. I had a friend back in college, and he was an electrical engineering student, and so he was good with circuits and stuff, and he wanted to learn programming. So, and he rode the bus, so he would ride home on the bus every night and read a book and trying to learn programming. And I kept trying to tell him, you know, that's not how you don't learn by memorizing that stuff out of a book. You know, you gotta, you know, practice it. So
Get car sick. Yeah. Okay, well, thank you so much.
Okay, thanks. See you next time. Take care.